The concept of nothingness is one of the most perplexing ideas in both science and philosophy. For centuries, human beings have grappled with the question of whether true nothingness could exist, and if it could, what its nature might be. This discussion becomes even more fascinating when we attempt to apply it to the origins of the universe itself. The phrase nothingness suggests a complete absence, no matter, no energy, no space, and no time. However, our current understanding of physics suggests that even what we perceive as nothing is, in fact, full of potential and energy. What existed before the Big Bang, if anything, remains an enigma. The concept of nothingness becomes central to our understanding of cosmology, especially in discussions about what might have existed before the birth of the universe. Many people think of the Big Bang as the beginning of everything. Time, space, matter, and energy all emerged from a singularity. Yet, cosmologists have theorized that there might have been a form of nothing that still had the potential to give rise to something. This view stands in contrast to classical definitions of a void and challenges our notions of what it means for something to emerge from nothing. In modern physics, particularly in quantum mechanics, nothingness is not empty. Even in a vacuum, particles and antiparticles can spontaneously appear and disappear, a phenomenon known as quantum fluctuations. This dynamic view of nothingness suggests that the universe could have been born from these minute fluctuations, leading to the explosive creation event we now call the Big Bang. Instead of viewing nothingness as a total void, quantum physics reveals that even nothing has structure, a sea of potential energy governed by the strange and often counterintuitive rules of quantum mechanics. Quantum fluctuations, a key concept in quantum mechanics, arise due to the inherent uncertainty of quantum states. In the quantum realm, particles do not exist as fixed, stable entities with precisely defined properties. Instead, they exist in a state of probability, where their location, momentum, and other characteristics can fluctuate unpredictably. These fluctuations are a natural consequence of the Heisenberg uncertainty principle, which dictates that certain pairs of physical properties, such as position and momentum, cannot be known with perfect accuracy at the same time. This principle implies that even in what we perceive as empty space, there is always some degree of uncertainty and spontaneous activity happening at the quantum level. What we traditionally think of as empty space, the vacuum, is not truly empty in the quantum sense. Instead, it is teeming with energy fluctuations and brief spontaneous appearances of virtual particles. These virtual particles constantly pop in and out of existence, borrowing energy from the vacuum itself. Though these particles exist only momentarily, their presence indicates that space is never entirely devoid of activity. This dynamic, ever-changing energy field is referred to as the quantum vacuum, which is far from the classical idea of a void. Quantum fluctuations in the vacuum are an essential feature of the fabric of space-time. In this context, the traditional notion of nothingness is radically transformed. Rather than being a barren emptiness, quantum mechanics reveals that what we perceive as empty space is actually a seething, fluctuating field of energy. This understanding challenges the classical notion of nothingness as an absolute absence of matter, energy, and activity. The idea that the universe itself could have emerged from quantum fluctuations presents a profound shift in our understanding of cosmic origins. Quantum fluctuations, as unpredictable and spontaneous events, could create conditions that lead to the formation of entire universes. In particular, these fluctuations might have triggered the Big Bang, sparking the rapid expansion of space and the creation of all the matter and energy we observe today. In this sense, the universe could have been born out of the quantum vacuum, a seemingly empty state that nevertheless has the potential to generate something as vast as a universe. Before the Big Bang, there may have been no recognizable matter or energy in the conventional sense, but the quantum vacuum would still have existed, filled with potential energy that could manifest as particles and other phenomena.
This vacuum would be governed by the principles of quantum mechanics, where particles and energy fields appear and disappear spontaneously. The notion that the universe could arise from such quantum fluctuations reshapes our understanding of nothingness, suggesting that nothing in the quantum sense is never truly empty or inactive.
This theory leads to the intriguing possibility that the universe could have spontaneously emerged from the quantum vacuum through the process of quantum tunneling or quantum genesis, where a sufficiently large fluctuation in the vacuum led to the birth of the universe. In this framework, the concept of creation itself is redefined. The universe could arise naturally from the inherent properties of the quantum vacuum without violating any physical laws. This quantum perspective on nothingness challenges both classical physics and philosophical notions of creation and existence. It suggests that the vacuum, which appears empty in classical terms, is in fact a rich, dynamic environment with the potential to give rise to entire universes. Therefore, the idea of nothingness in quantum mechanics is not a true void, but a fertile ground for cosmic creation, offering a revolutionary way to think about the origin of the universe and the nature of existence itself. The birth of the universe from this fluctuating quantum nothingness presents a profound challenge to classical metaphysical ideas about creation. In classical philosophy, nothing was seen as the absolute absence of being. But quantum mechanics and cosmology suggest that nothing may never be truly empty. This realization reshapes the fundamental debate about the universe's origin. If nothing is not really empty, then it is easier to imagine how the universe could have emerged without violating physical laws. It also implies that creation might be a natural process rather than a miraculous event. In addition to the quantum vacuum hypothesis, cosmologists have proposed other explanations for what might have existed before the Big Bang. One of the most compelling ideas is cosmic inflation. According to this theory, the very early universe underwent a period of rapid and exponential expansion immediately following the Big Bang. Though inflation primarily explains what happened after the Big Bang, it provides clues about the conditions that might have existed prior to it. During inflation, the universe expanded faster than the speed of light, smoothing out any irregularities and setting the stage for the formation of galaxies and other cosmic structures. This inflationary period hints at what might have been occurring before the universe we know came into existence. Cosmic inflation also supports the notion that our universe could be part of a larger multiverse. If inflation can happen in one region of space, leading to the creation of a universe, it might occur in other regions, spawning countless other universes with different physical laws. This idea leads to the tantalizing possibility that what we think of as nothing could be a realm where inflationary bubbles continuously form, each giving birth to a new universe. In this scenario, the Big Bang might not have been a unique event, but one of countless similar explosions in an eternal cycle of universe creation. The theory of inflation, proposed in the early 1980s by physicist Alan Guth, offers an explanation for some of the most puzzling aspects of the early universe, such as its apparent uniformity, flatness, and lack of magnetic monopoles. Inflation suggests that, in the first tiny fraction of a second after the Big Bang, roughly around 10 to the power of negative 36 to 10 to the power of negative 32 seconds, the universe underwent an exponential expansion. During this period, space expanded faster than the speed of light, smoothing out any irregularities and stretching quantum fluctuations to cosmic scales, which eventually seeded the formation of galaxies. Inflation theory is rooted in the idea that the universe's energy was dominated by the so-called vacuum energy, a form of energy associated with empty space itself. This vacuum energy is thought to have driven the universe's rapid expansion by exerting a repulsive gravitational force, which caused space to stretch exponentially. As a result, inflation expanded the universe by an unimaginable factor in an extremely brief period of time, resolving several problems that the traditional Big Bang model couldn't fully explain. One of the problems that inflation solves is the horizon problem. This refers to the observation that different regions of the universe, which are so far apart that they could never have exchanged information or energy, nonetheless appear to have nearly identical temperatures and properties. Inflation explains this by suggesting that all regions of the universe were once much closer together before they were blown apart by the rapid expansion, allowing them to reach thermal equilibrium before inflation stretched space. Another issue inflation addresses is the flatness problem, which refers to the observation that the universe appears to be geometrically flat on large scales. In a flat universe, the angles of a triangle add up to 180 degrees, and parallel lines never meet. Inflation stretches space so much that any initial curvature the universe may have had would have been flattened out, leaving the universe nearly flat, as observations suggest it is today. While inflation theory provides a compelling explanation for many of the early universe's mysteries, it leaves open significant questions, particularly regarding what triggered inflation in the first place. According to the theory, inflation was driven by a form of vacuum energy, but the exact nature of this energy and the mechanism that caused inflation to start remains unclear. One hypothesis is that inflation could have been triggered by a high-energy scalar field, sometimes referred to as the inflaton field. This field would have permeated space during the early universe, with its energy driving the exponential expansion. However, the exact properties of this field and why it suddenly began to dominate the universe's energy remain topics of active research. Another question is what caused inflation to end. As the universe expanded during inflation, the energy of the vacuum would have decreased, eventually leading to a phase transition, where the vacuum energy was converted into particles and radiation. This process, known as reheating, filled the universe with the matter and radiation that would later form galaxies, stars, and planets. However, what precisely caused this transition and why the inflationary phase ended are still open questions in cosmology. Moreover, inflation theory raises deep questions about what might have existed before the inflationary phase. In the standard inflationary model, time itself may have begun with the Big Bang, and before inflation, the universe could have been in a chaotic high-energy state with no clearly defined structure. However, other models suggest that inflation may not have been the beginning of time. Some versions of inflationary theory propose that inflation is eternal, meaning that while inflation may have ended in our observable universe, it could continue indefinitely in other regions of space, constantly spawning new, bubble universes in a larger multiverse. In this multiverse scenario, our universe is just one of many, and inflation is a perpetual process that happens randomly across different parts of the multiverse. This raises the possibility that there was no singular beginning to inflation or to the universe itself, but rather that inflation has been going on forever in some form, giving rise to countless different universes with their own properties and laws of physics. The question of what, if anything, existed before inflation remains a profound mystery. If time itself began with the Big Bang and inflation, then the concept of before may not make sense in the way we typically understand it. However, some cosmologists are exploring the possibility that the universe underwent different phases before inflation, or that inflation was just one stage in an even larger cosmic process. One such idea is the cyclic model, which suggests that the universe goes through endless cycles of expansion and contraction, with inflation being one part of a recurring cosmic cycle. While inflation theory has revolutionized our understanding of the early universe and solved several key puzzles, it also opens up new questions about the fundamental nature of the universe. What triggered inflation? What existed before it? And whether inflation is part of a larger multiverse are questions that continue to drive research in cosmology, pushing the boundaries of our understanding of the cosmos. In cosmology, the concept of a singularity presents a profound challenge to our understanding of the universe's origins. In the framework of the standard Big Bang model, the universe is thought to have emerged from a singularity, a point of infinite density where all matter and energy were concentrated into an extraordinarily small space. At this point, the gravitational forces were so intense that the laws of physics, particularly general relativity and quantum mechanics, no longer apply in a comprehensible way. This is because, at such extreme conditions, space and time themselves become infinitely warped, leading to a breakdown in our current understanding of how the universe operates. The singularity represents a moment when the very fabric of space and time collapses into a single dense point. At this point, the universe's temperature and density become infinite, and all of the known forces, including gravity, unify into a state we cannot currently describe with existing theories. This presents a significant dilemma for cosmologists, because the physical laws that normally govern the behavior of matter and energy fail to make sense under these extreme conditions. As a result, the singularity is often seen as a boundary of knowledge, a point beyond which our current understanding of physics cannot extend. One of the most perplexing aspects of the singularity is its implications for the concept of time. According to the theory of general relativity, time is not separate from space, but is intrinsically linked to it in what we call spacetime. As we approach the singularity, space-time itself becomes so distorted that the usual flow of time breaks down. This means that talking about before the Big Bang may be meaningless, as time as we understand it does not exist before the expansion of the universe begins. In other words, the singularity is not just a point in space, but also a point in time, where the conventional ideas of past, present, and future cease to hold. The very concept of a before the Big Bang is problematic because in the context of the singularity, time itself starts with the Big Bang. Prior to this event, if time didn't exist in a form we can comprehend, asking what happened before becomes nonsensical within our current physical theories. Thus, the singularity marks not only the beginning of the observable universe, but also the beginning of time as we know it. This leaves us with a profound philosophical and scientific question. If time and space began with the Big Bang, how can we conceptualize or describe anything beyond or before this moment? The singularity presents a mystery that challenges the limits of both physics and metaphysics, pushing us toward new theories, such as quantum gravity or string theory, to better understand the true nature of the universe's origins. The notion that the universe began from a singularity challenges the very concept of causality. If time did not exist before the Big Bang, can we even talk about a cause that led to the universe's existence? In this framework, the universe simply came into being without any cause, as the concept of before becomes meaningless when applied to the singularity. Some physicists argue that trying to understand what happened before the Big Bang is like asking what is north of the North Pole. The question itself is nonsensical because time, as we understand it, did not exist before the event. The idea of a singularity also opens the door to various alternative models of the universe. One such model is the cyclic or oscillating universe theory. According to this theory, the universe undergoes endless cycles of expansion and contraction. In this model, the Big Bang was not the beginning of time, but rather the beginning of one cycle in a much larger process. After expanding for billions of years, the universe would eventually stop, reverse course, and collapse back into a hot, dense state in what is known as the Big Crunch. This collapse would then lead to another Big Bang, and the cycle would begin anew. In the cyclic model, time does not have a definite beginning or end. Instead, the universe goes through repeated cycles of creation and destruction. This theory has been supported by certain interpretations of string theory, which suggest that the universe could avoid the singularity entirely by bouncing from a contracting phase into an expanding one. In this scenario, what we think of as the Big Bang might have been just one event in an eternal sequence of bounces. The cyclic model provides an elegant solution to the question of what existed before the Big Bang, because it implies that there was no absolute beginning. Time, in this model, stretches back infinitely into the past, with each universe born from the remnants of the one before. This model also suggests that the laws of physics, as well as the constants that govern the behavior of matter and energy,
might change from one cycle to the next. Each new universe could have slightly different physical characteristics, leading to endless variation over infinite time. One of the strengths of the cyclic model is that it avoids the problem of the singularity. By proposing that the universe bounces rather than collapses into a singularity, the cyclic model maintains the continuity of time and space, even during the transition between cycles. This makes it easier to conceptualize a before the Big Bang, as the universe would have simply been in a previous contraction phase.
The cyclic model also aligns with recent developments in quantum gravity, which seeks to reconcile general relativity with quantum mechanics. One of the challenges in modern cosmology is that the theory of general relativity, which describes the large-scale structure of the universe, breaks down at the singularity. Quantum gravity offers the possibility of a more complete theory that could describe what happens at extremely high densities and temperatures, such as those found in the early universe. By combining the principles of quantum mechanics with gravity, scientists hope to better understand the conditions that led to the Big Bang and whether the universe has a cyclical nature. In recent years, advances in observational cosmology have provided new insights into the early universe. The discovery of cosmic microwave background radiation, the afterglow of the Big Bang, has allowed scientists to study the conditions that existed just 380,000 years after the universe's birth. This radiation provides a snapshot of the universe when it was still in its infancy, and by studying its variations, scientists can gain insights into the processes that shaped the universe's evolution. The study of the cosmic microwave background has revealed that the universe is remarkably uniform on large scales, with only tiny fluctuations in temperature and density. These fluctuations are believed to have been seeded by quantum fluctuations during the inflationary period, which were then amplified as the universe expanded. This discovery supports the theory of inflation and suggests that quantum mechanics played a crucial role in the early stages of the universe's development. As scientists continue to probe the origins of the universe, the question of what existed before the Big Bang remains one of the most profound mysteries in cosmology. Whether the universe arose from quantum fluctuations, a singularity, or a previous cosmic cycle, the concept of nothingness challenges our deepest assumptions about the nature of existence. The origin of the universe is one of the most profound and perplexing questions humanity has ever faced. While the Big Bang theory provides the dominant explanation for how the universe began, it does not definitively explain what caused the universe to exist in the first place, or what, if anything, existed before the Big Bang. Several theoretical frameworks have emerged to address these questions, each offering unique perspectives on the universe's origins. Among these are the multiverse theory, the role of quantum fluctuations, and the influence of quantum mechanics on the universe's creation. This chapter will explore these ideas, as well as the tantalizing concept that the universe might have emerged from a chaotic bubbling of cosmic possibilities. The multiverse theory has gained significant traction in recent years as a way to explain not only the origin of our universe, but also the apparent fine-tuning of the physical laws that govern it. According to this theory, our universe may be just one of many universes, each with its own distinct set of physical laws and constants. This collection of universes is often referred to as the multiverse. The idea of a multiverse is particularly appealing to cosmologists because it provides an explanation for why the physical constants in our universe seem so finely tuned to allow for the existence of life. In the context of the multiverse, the Big Bang that created our universe may have been just one of countless similar events occurring in other regions of space, each giving rise to a separate universe with its own unique properties. This concept is sometimes referred to as the bubble universe or pocket universe model, in which each universe forms like a bubble in a vast cosmic sea. Some bubbles might pop into existence, while others might collapse, disappear, or evolve into fully formed universes like ours. The concept of the multiverse offers a compelling explanation for the apparent fine-tuning of the physical constants in our universe. Fine-tuning refers to the observation that the fundamental forces and constants of nature, such as the strength of gravity, the electromagnetic force, and the rate of cosmic expansion, are precisely calibrated to allow for the existence of galaxies, stars, planets, and life as we know it. Even slight deviations in these constants would result in a universe that either expands too quickly for structures to form, collapses back into itself, or prevents the formation of complex chemistry needed for life. The multiverse theory suggests that instead of one singular universe with finely tuned physical constants, there could be an infinite or near-infinite number of universes, each with its own set of physical laws and constants. In such a multiverse, the values of these constants vary randomly from one universe to another. Some universes might have conditions that are too extreme for the formation of stars or galaxies, while others could have physical constants that prevent life from evolving. In this context, the fine-tuning of our universe is no longer seen as improbable or extraordinary, but rather as a natural consequence of the vast number of universes that could exist. In this view, our universe is simply one of many where the conditions happen to be just right for life to emerge. Since only universes with suitable conditions for life would have observers capable of asking why the universe appears fine-tuned, this observation is biased. It's known as the anthropic principle. According to this principle, we find ourselves in a universe where the constants allow for life, because if the constants were different, we wouldn't be here to ask the question in the first place. Other universes within the multiverse may have drastically different physical constants, resulting in realities where life, as we understand it, is impossible. For example, a universe with a much stronger gravitational constant might collapse before stars and planets can form, or one with weaker electromagnetic forces might fail to support complex atomic structures. In this way, the multiverse concept sidesteps the need for a single finely tuned universe by proposing a vast ensemble of universes, each with its own set of natural laws. This idea has significant implications for our understanding of the universe and the search for meaning within it. Rather than seeing our universe as uniquely special or designed with life in mind, the multiverse theory implies that life exists in this universe simply because the physical constants happen to allow it. This eliminates the need for a deliberate fine-tuning mechanism and suggests that our universe's conditions are a result of statistical probability across an enormous multiverse. Though the multiverse theory offers an intriguing explanation for the fine-tuning problem, it remains speculative. Direct evidence for the existence of other universes is currently lacking, and the multiverse itself may be beyond the reach of empirical verification. Nevertheless, the multiverse concept continues to provide a thought-provoking framework for addressing some of the deepest questions about the nature of our universe and the possibility of alternative realities where life, as we know it, cannot exist. One of the key predictions of the multiverse theory comes from the idea of cosmic inflation. According to the theory of inflation, the universe underwent a rapid expansion shortly after the Big Bang. This inflationary period stretched spacetime so rapidly that quantum fluctuations were blown up to cosmic scales, seeding the formation of galaxies and other large-scale structures. In some versions of the inflationary model, inflation never truly ends. It continues in some regions of space, constantly creating new bubble universes. Our universe in this framework is just one of many bubbles in an ever-expanding cosmic landscape. While the multiverse theory is compelling, it also presents some significant challenges. One of the biggest difficulties is that, by definition, other universes in the multiverse are beyond our observational reach. If these universes are separate from ours, then we cannot observe or interact with them, making it impossible to test the multiverse hypothesis directly. This has led some critics to argue that the multiverse is more of a philosophical idea than a scientific theory, as it lacks empirical falsifiability. Despite these challenges, the multiverse remains a popular explanation for the origins of the universe, particularly because it offers a way to address some of the most perplexing questions in cosmology. If the multiverse exists, it could help explain not only the fine-tuning of physical constants, but also the apparent randomness of quantum events in our universe. In a multiverse, different outcomes of quantum events might play out in different universes, with every possibility realized somewhere in the vast expanse of the multiverse. Quantum fluctuations play a crucial role in many theories of the universe's origin, particularly in the context of the Big Bang and the inflationary model. Quantum fluctuations are random changes in energy that occur at the smallest scales of existence, where the laws of quantum mechanics dominate. These fluctuations are an inherent part of quantum fields, and they can give rise to particles and antiparticles that appear and disappear in a vacuum. Even in empty space, quantum fluctuations are constantly occurring, causing tiny temporary changes in energy levels. In the early universe, quantum fluctuations were stretched to macroscopic scales during the inflationary period. These fluctuations in energy density are thought to have provided the seeds for the formation of galaxies and other large-scale structures in the universe. As space expanded rapidly during inflation, small quantum fluctuations became large enough to influence the distribution of matter and energy in the universe. This process helps explain why the universe is not perfectly uniform, but instead contains clusters of galaxies separated by vast voids of empty space. The idea that quantum fluctuations could lead to the formation of entire universes has also been explored in the context of the multiverse theory. If inflation is eternal, then quantum fluctuations in the inflationary field could trigger the creation of new bubble universes in different regions of space. Each bubble universe would have its own distinct physical laws, potentially giving rise to entirely different realities. This process of universe creation is sometimes referred to as quantum genesis, as it suggests that quantum fluctuations are the driving force behind the birth of new universes. Quantum fluctuations also challenge our classical understanding of reality. In classical physics, objects have definite positions and velocities, and events unfold in a predictable, deterministic manner. However, in quantum mechanics, particles exist in a state of probability until they are observed or measured. This leads to the famous observer effect, in which the act of measurement affects the outcome of a quantum event. In this view, reality at the quantum level is not fixed, but dynamic, constantly fluctuating between different possibilities. This dynamic nature of reality raises profound questions about the nature of existence. If quantum fluctuations can create particles out of nothing, could they also create entire universes? And if so, what does that say about the nature of nothingness and the origins of our universe? These questions are at the heart of many modern cosmological theories, which seek to understand how the universe could have emerged from a quantum vacuum, a state of nothingness that is still full of potential. Quantum mechanics plays a crucial role in shaping our understanding of the universe's origins, particularly in the context of the Big Bang and what might have existed before it. This branch of physics focuses on the behavior of particles at the smallest scales, such as electrons, quarks, and photons, where the laws of classical mechanics no longer apply. Instead of behaving in predictable ways, as larger objects do, particles at the quantum level exhibit behaviors that seem counterintuitive and unpredictable to our everyday experience. One of the foundational principles of quantum mechanics is the concept of uncertainty. This idea, encapsulated by Heisenberg's uncertainty principle, states that certain pairs of properties, like a particle's position and momentum, cannot both be precisely known at the same time. The more accurately you know one property, the less accurately you can know the other. This uncertainty introduces a fundamental element of unpredictability at the quantum level, where particles don't have fixed positions or velocities until they are measured or observed. This uncertainty also leads to another strange quantum phenomenon: superposition. In a state of superposition, particles can exist in multiple states or locations simultaneously. For instance, an electron can be in different energy levels at once, and it is only when we observe or measure the particle that it collapses into one specific state. This behavior defies classical intuition, where we expect objects to have definite properties at any given time. In the context of the universe's beginning, quantum mechanics introduces the possibility that the universe itself may have originated from a quantum fluctuation, a brief, spontaneous change in energy that occurs even in empty space. Even in a vacuum, quantum mechanics predicts that energy fields are never truly zero. Instead, they experience tiny fluctuations that allow for particles to pop in and out of existence. This concept is central to the idea that the universe might have emerged from a quantum vacuum, a state that is not completely nothing, but rather a bubbling cauldron of potential energy. During the Big Bang, quantum fluctuations could have played a significant role in shaping the initial conditions of the universe. These fluctuations, though incredibly tiny, were stretched to cosmic scales during the period of cosmic inflation, giving rise to the seeds of structure we observe today, such as galaxies and clusters of galaxies. Quantum mechanics helps explain how these fluctuations could have led to slight variations in the density of matter and energy, which later grew into the cosmic structures that form the large-scale universe we observe. Additionally, quantum mechanics challenges the notion of a classical singularity at the beginning of time. In classical physics, the Big Bang singularity is seen as a point where density and temperature become infinite, leading to a breakdown of the known laws of physics. However, quantum mechanics introduces the possibility that this singularity may not be a true point in space and time. Instead, quantum effects could have prevented the universe from collapsing into a singularity altogether, providing a more nuanced explanation for what happened at or before the Big Bang. The idea that the universe could have emerged from a quantum state also blurs the line between existence and non-existence. In classical physics, the universe would need a cause to bring it into being, but in quantum mechanics, the universe could spontaneously arise from the vacuum without violating any physical laws. This has led to the hypothesis that the universe might have tunneled into existence through a quantum process, where the quantum vacuum fluctuated in such a way that it sparked the rapid expansion of spacetime, giving rise to the universe as we know it. Quantum mechanics provides a framework for understanding how the universe could have emerged from seemingly nothing, and how the extreme conditions of the early universe shaped its evolution. The principles of uncertainty, superposition, and quantum fluctuations suggest that the early universe was a dynamic and unpredictable place, governed by the laws of quantum physics rather than classical mechanics. This leads to profound implications for our understanding of the origins of the universe and what might have existed before the Big Bang, indicating that the true nature of the universe's birth may lie within the strange and counterintuitive realm of quantum phenomena. In the context of the early universe, quantum mechanics provides a framework for understanding the extreme conditions that existed just after the Big Bang. At the moment of the Big Bang, the universe was incredibly hot and dense, with temperatures reaching billions of degrees. Under these conditions, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified, and quantum effects dominated the behavior of particles. One of the key challenges in modern cosmology is reconciling quantum mechanics with general relativity, which describes the behavior of gravity at large scales. While general relativity works well for explaining the structure of the universe at cosmic scales, it breaks down at the singularity, the point of infinite density that marks the beginning of the Big Bang. Quantum mechanics, on the other hand, provides a framework for understanding the behavior of matter and energy at the smallest scales, but struggles to explain how gravity fits into the picture. To resolve this tension, physicists have developed theories such as string theory and loop quantum gravity, which attempt to unify quantum mechanics with gravity. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but rather tiny vibrating strings. These strings exist in multiple dimensions, and their interactions give rise to the particles and forces we observe in the universe. In this framework, the Big Bang may have been the result of the collision of higher dimensional branes, short for membranes, leading to the creation of a new universe. Loop quantum gravity, another approach to unifying quantum mechanics with gravity, suggests that space and time themselves are quantized, meaning they are made up of tiny, discrete units rather than being continuous. In this view, the universe did not emerge from a singularity, but rather underwent a quantum bounce, where a previous contracting phase gave way to a new expanding phase. This idea aligns with the cyclic model of the universe, in which the Big Bang was not the beginning of time, but rather a transition between cosmic cycles. Quantum mechanics also plays a crucial role in understanding the chaotic nature of the early universe. The Big Bang was not a smooth, orderly event. It was chaotic and turbulent, with quantum fluctuations shaping the distribution of matter and energy. This chaotic bubbling of cosmic possibilities is a central theme in many theories of the universe's origin, as it suggests that the universe we observe today is just one of many possible outcomes of the initial conditions set by the Big Bang. The idea that the universe could have emerged from a chaotic sea of quantum fluctuations challenges our classical understanding of causality and determinism. In classical physics, every event has a cause, and the future is determined by the past. But in quantum mechanics, the future is not predetermined. It is a realm of probabilities and possibilities, where different outcomes can coexist until they are observed. This view of reality has profound implications for our understanding of the universe's origins, as it suggests that the universe could have emerged from a chaotic, indeterminate state rather than a fixed, preordained one. The chaotic nature of the early universe also raises questions about the role of chance in the universe's formation. If quantum fluctuations played a key role in shaping the universe, then the existence of galaxies, stars, and even life itself may be the result of random chance events. This view challenges traditional notions of a deterministic, clockwork universe and suggests that randomness and chaos are fundamental aspects of the cosmos. The theories of the universe's origins explored in this chapter offer a fascinating glimpse into the complex and mysterious processes that gave rise to the cosmos. The multiverse theory suggests that our universe is just one of many, each with its own unique set of physical laws and constants. Quantum fluctuations and quantum mechanics provide a framework for understanding the dynamic nature of reality and the role of chance in the universe's formation. Finally, the chaotic bubbling of cosmic possibilities challenges our classical understanding of causality and determinism, offering a new perspective on the origins of the universe and the nature of existence itself. The notion of the multiverse, the idea that our universe is just one of countless others, represents one of the most intriguing and bold concepts in modern cosmology. This theory has emerged in an attempt to address fundamental questions that traditional Big Bang cosmology cannot fully explain, such as the fine-tuning of physical constants, the ultimate fate of the universe, and what might have existed before the Big Bang. In exploring the multiverse, we delve into possibilities that stretch our understanding of physics, space, and time. The multiverse introduces an entirely new perspective on the nature of reality, where universes may be born from collisions, physical laws differ across realms, and quantum fluctuations shape the birth of multiple universes. The concept of universes born from collisions is an idea rooted in a variation of string theory called brane cosmology. According to this theory, our universe exists on a three-dimensional membrane, or brane, that floats in a higher dimensional space known as the bulk. In this higher dimensional framework, other branes may exist, each representing a different universe. These branes can interact with each other, and one of the most intriguing possibilities is that our universe was born from the collision of two branes within the bulk. The idea of universes forming from collisions between branes offers an alternative to the traditional Big Bang scenario. Rather than envisioning the universe's origin as a singularity, where all matter and energy were concentrated at a single point, brane cosmology suggests that the Big Bang was the result of a violent collision between two branes. This collision released an immense amount of energy, which in turn created the conditions necessary for the birth of a new universe. In this view, our universe is one of many that could arise from such interactions. The brain collision model is an example of what is known as the ekpyrotic universe, named after the ancient Greek word ekpyrosis, meaning conflagration or destruction by fire. This theory suggests that the universe goes through periodic cycles of creation, where brain collisions trigger new Big Bang events. These events give rise to new universes with different properties, allowing for the possibility of an infinite series of universe births, each with its own distinct characteristics. One of the strengths of the brain collision model is that it provides a natural explanation for the fine-tuning of the universe's physical constants. In a multiverse where different universes are born from collisions, each universe might inherit slightly different physical laws and constants from the brains that created it. This diversity of universes allows for a wide range of possibilities, some of which might have conditions that are conducive to the formation of galaxies, stars, and life, while others may be completely inhospitable. Another compelling aspect of the brain collision model is that it eliminates the need for a singularity at the beginning of time. In traditional Big Bang cosmology, the universe begins as a singularity, a point of infinite density and temperature, where the laws of physics break down. But in the brain collision model, the Big Bang is not the beginning of time. It is simply the result of a collision between two pre-existing brains. This removes the need for an initial singularity and allows time to extend infinitely into the past and future, with universes being born from repeated brain collisions. In the multiverse, different universes may operate under different sets of physical laws and constants. This diversity across universes is one of the key features of the multiverse hypothesis, and it has profound implications for our understanding of physics and cosmology. While our universe is governed by specific physical constants, such as the gravitational constant, the speed of light, and the strength of the electromagnetic force, other universes might have entirely different constants that lead to vastly different realities. One of the most significant questions that the multiverse addresses is the issue of fine-tuning. Our universe appears to be fine-tuned for the existence of life. The values of the physical constants are precisely what they need to be to allow for the formation of stable matter, stars, and planets. If any of these constants were even slightly different, the universe would either collapse in on itself or expand too quickly for galaxies and stars to form. The multiverse offers a potential explanation for this fine-tuning. If there are an infinite number of universes, each with different physical constants, it is not surprising that at least one of them would have the right conditions for life. In this view, the apparent fine-tuning of our universe is simply a result of selection bias. We exist in a universe that allows for life because, in all the other universes where the constants are not conducive to life, no one is around to observe them. This idea of varying physical laws across the multiverse also opens up new avenues of scientific inquiry. For example, some versions of string theory suggest that different regions of the multiverse could have different numbers of dimensions, different types of fundamental forces, or even different forms of matter. These differences could lead to universes that are unrecognizable to us, with completely alien physical properties. In some universes, gravity might be much stronger or weaker than it is in our own, leading to entirely different cosmic structures. In others, the speed of light might be slower, or particles might interact through forces that we do not experience. The sheer diversity of possibilities within the multiverse is staggering, and it raises profound questions about the nature of reality itself. The multiverse theory also provides clues about what might have existed before the Big Bang. In traditional cosmology, the Big Bang marks the beginning of time, space, and matter. However, in the context of the multiverse, the Big Bang might not have been the beginning of everything. It may have been just one event in a much larger and more complex cosmic process. One of the key insights that the multiverse provides is that the Big Bang could have been the result of quantum fluctuations in a pre-existing multiverse. In this view, our universe was born out of a quantum vacuum, a state of nothingness that still contains the potential for creation. This quantum vacuum may have existed before the Big Bang and could have given rise to not just our universe, but countless others as well. Some cosmologists believe that the multiverse can help explain the origin of the universe by suggesting that the Big Bang was not a unique event. Instead, the multiverse is constantly giving birth to new universes through processes such as quantum fluctuations or brane collisions. In this framework, time does not begin with the Big Bang. It stretches infinitely into the past, with universes constantly being created and destroyed in an endless cycle. The idea that the multiverse existed before the Big Bang also challenges our understanding of what nothingness means. In traditional cosmology, the Big Bang is seen as the beginning of everything, with nothing existing before it. But in the multiverse theory, there may have been a pre-existing state of potential where universes could emerge from quantum fluctuations or brane interactions. This challenges the classical notion of a singular beginning and suggests that the universe's birth may be part of a much larger cosmic process. Quantum fluctuations are a key component in many multiverse theories, particularly in the context of cosmic inflation. During the inflationary period that followed the Big Bang, the universe expanded at an exponential rate, causing quantum fluctuations in energy density to be stretched to cosmic scales. These fluctuations provided the seeds for the formation of galaxies and other large-scale structures in the universe. In the context of the multiverse, quantum fluctuations may not only explain the structure of our universe, but also the creation of multiple universes. According to the theory of eternal inflation, inflation never truly ends. While inflation may have stopped in our region of space, allowing the universe to cool and form galaxies, it continues in other regions, creating new bubble universes that each have their own distinct properties. These bubbles are formed by quantum fluctuations in the inflationary field, which trigger the creation of new universes. This process of universe creation through quantum fluctuations is known as quantum genesis. It suggests that quantum fluctuations are the driving force behind the birth of multiple universes within the multiverse. Each time a quantum fluctuation occurs in the inflationary field, it creates a new bubble universe, with its own unique set of physical laws and constants. This process could continue indefinitely, with new universes being born from quantum fluctuations in different regions of the multiverse. The role of quantum fluctuations in the multiverse also raises important questions about the nature of reality. In quantum mechanics, particles do not have definite positions or velocities until they are observed or measured. Instead, they exist in a state of probability, where multiple outcomes are possible. This leads to the idea of quantum superposition, where particles can exist in multiple states at once. In the context of the multiverse, this idea of superposition may extend to entire universes. Just as particles can exist in multiple states, so too can universes exist in multiple possible configurations. Each quantum fluctuation in the inflationary field creates a new universe with its own set of possibilities, leading to a vast and diverse multiverse where every possible outcome is realized somewhere. This view of the multiverse challenges our classical understanding of causality and determinism. In a multiverse where quantum fluctuations constantly create new universes, the future is not predetermined. Instead, it is a realm of infinite possibilities, where different outcomes can coexist in different universes. This challenges the traditional notion of a single, fixed reality, and suggests that the universe we observe is just one of many possible outcomes of quantum fluctuations. Exploring the multiverse and other universes opens up a new frontier in cosmology, one where the boundaries of space, time, and reality are stretched to their limits. Universes born from collisions between branes, different physical laws across universes, and the role of quantum fluctuations in creating multiple universes all point to a multiverse that is far more complex and diverse than anything we can observe directly. While the multiverse theory remains speculative and difficult to test, it offers a tantalizing glimpse into the possibilities that lie beyond our universe, challenging our understanding of the cosmos and the nature of existence itself. One of the most enduring questions in cosmology is whether the universe had a singular beginning, or whether it goes through an endless cycle of birth, death, and rebirth. The cyclical universe theory proposes that the universe undergoes repeated cycles of expansion and contraction, a process that may avoid the singularity problem posed by the Big Bang and offer a solution to what might have existed before it. This theory presents an alternative to the traditional view of a universe with a singular beginning and challenges the notion of a final end. Instead, the cyclical universe posits a universe in constant flux, eternally shaped by cycles of creation and destruction. This chapter explores the key ideas behind this theory, including the expansions and contractions of the universe, the oscillating universe model, the concept of a cosmic bounce, and the cycles of destruction and renewal that may characterize the universe's evolution. The concept of a cyclic universe, where the cosmos undergoes repeated phases of expansion and contraction, has been a part of both ancient philosophical and modern scientific thought. This idea posits that the universe does not have a definitive beginning or end, but instead exists in an eternal cycle of birth, death, and rebirth. It is a view deeply embedded in many ancient traditions, such as Hindu cosmology, which describes the universe as progressing through endless cycles of creation, preservation, and destruction, known as kalpas. Each kalpa represents a massive period of time, after which the universe is destroyed and then recreated, continuing the eternal cosmic rhythm. This ancient idea resonates with modern cosmological models that propose similar cyclic processes. In these scientific models, the universe undergoes phases where it expands, reaches a maximum size, and then contracts under the force of gravity, culminating in a big crunch, where all matter and energy collapse into an extremely dense state. From this high-density state, the cycle could begin anew with another Big Bang-like event, initiating a new phase of expansion. In this way, the universe continually oscillates between expansion and contraction phases, with no true beginning or end to time. The modern cyclic universe theories build on principles from both general relativity and quantum mechanics, offering an alternative to the traditional Big Bang model, which posits that the universe began as a singularity and will continue to expand indefinitely. The cyclic model avoids the problem of an absolute beginning, instead suggesting that what we perceive as the beginning of the universe was merely the start of the current cycle. Before this phase, the universe may have been contracting, with time and space continuing into the past through countless previous cycles. One of the scientific motivations for exploring cyclic models is the idea that they can address certain challenges posed by the standard cosmological model, such as the issue of entropy. In classical thermodynamics, entropy, a measure of disorder, increases over time in a closed system, which implies that the universe should gradually approach a state of maximum entropy, known as heat death, where all processes cease. However, in a cyclic universe, each new cycle could reset the entropy levels, allowing the universe to start over in a low entropy state after each collapse and bounce, thereby avoiding the problem of heat death. The cyclic universe theory also finds parallels in modern physics through concepts like brane cosmology, which emerges from string theory. In these models, our universe exists on a three-dimensional membrane, or brane, within a higher dimensional space. Periodically, branes in this higher dimensional space could collide, releasing enormous amounts of energy and triggering a new Big Bang, which initiates another phase of expansion in our universe. After the expansion phase, the universe could eventually contract again, leading to another cycle of brane collision and universe formation. This process could continue indefinitely, creating an eternal cycle of universe creation and destruction. In these modern interpretations, the cycles of expansion and contraction offer a way to avoid the singularity that appears in the traditional Big Bang model. Rather than the universe starting from an infinitely dense point, the cyclic model suggests that the universe bounces back from a previous contraction phase, never actually reaching the singularity. This cosmic bounce represents the transition between the contraction and expansion phases and prevents the universe from collapsing into a singular point of infinite density. Cyclic models of the universe also offer an interesting philosophical perspective, aligning with the idea that time may not have a beginning or end, but is instead a continuous process. This stands in contrast to the linear conception of time found in many Western cosmological models, where the universe has a definite starting point in the Big Bang and will eventually reach a final state, whether that be a big freeze, big rip, or big crunch. The cyclic view suggests that time extends infinitely into the past and future, with the universe constantly evolving through cycles of creation and destruction. The idea that the universe expands and contracts in a cyclic manner connects ancient philosophical traditions with cutting-edge modern science. From Hindu cosmology's Kalpas to the latest models in string theory and quantum cosmology, the notion of a cyclic universe challenges our understanding of time, existence, and the ultimate fate of the cosmos. Whether or not the universe truly operates in this way remains an open question, but the idea of a cosmos that endlessly renews itself through cycles offers a profound alternative to the traditional, linear view of cosmic history. In the cyclical universe theory, the current expansion of the universe, which began with the Big Bang, will eventually slow down due to gravitational forces. Once the expansion halts, the universe will reverse its course and begin contracting, drawing all matter and energy back toward a singular dense state. This contraction phase, often referred to as the Big Crunch, represents the end of one cosmic cycle. However, instead of being the final end, the universe undergoes a bounce that leads to a new expansion, much like the Big Bang, but without the need for a singularity. The idea of cosmic contraction offers an alternative explanation for the fate of the universe compared to the widely accepted model of an eternally expanding universe driven by dark energy. In the standard model, dark energy causes the universe's expansion to accelerate, leading to a big freeze or heat death, where the universe continues expanding indefinitely and all stars eventually burn out, leaving a cold and empty cosmos. The cyclical model, however, suggests that this expansion is not permanent and that gravitational forces will eventually overcome dark energy, causing the universe to collapse back into itself. The idea of oscillating expansions and contractions offers a more dynamic view of the universe, where its fate is not determined by an inevitable heat death, but by a repeating pattern of cosmic evolution. In this model, the universe undergoes alternating phases of growth and decay, each cycle driven by the fundamental forces of nature. The expansion phases are similar to the Big Bang we observe today, while the contraction phases reverse this process, leading to the eventual rebirth of the universe. The oscillating universe model was first proposed in the early 20th century by scientists such as Albert Einstein and Richard Tolman, who speculated that the universe might not be static, but could oscillate between periods of expansion and contraction. Einstein initially believed in a static universe, but when he applied general relativity to cosmology, he discovered that a static universe was not stable. This led to the development of the dynamic universe model, where the universe could expand and contract over time. Richard Tolman expanded on this idea by suggesting that the universe might oscillate between big bangs and big crunches, with each cycle resetting the universe. Tolman's model, known as the oscillating universe, introduced the idea that the universe has no true beginning or end, but is instead a continuous process of creation and destruction. According to this model, each contraction phase ends with a bounce, initiating a new expansion, much like the current Big Bang. One of the appealing aspects of the oscillating universe model is that it avoids the need for a singularity. a point of infinite density where the laws of physics break down. In the standard Big Bang model, the universe began as a singularity, an infinitely small and dense point where time, space, and the physical laws as we know them did not exist. The oscillating universe model, however, suggests that the universe never actually reaches a singularity. Instead, when the universe contracts to a certain point, quantum effects come into play, causing a bounce that leads to the next phase of expansion. The oscillating universe model has evolved over time, incorporating new discoveries in physics and cosmology. For example, recent developments in string theory and loop quantum gravity have provided new insights into how the universe might avoid singularities during the contraction phase. In string theory, the universe is composed of tiny, vibrating strings that exist in multiple dimensions. These strings may prevent the universe from collapsing into a singularity by introducing new forces that cause the universe to bounce back into an expansion phase. Similarly, loop quantum gravity suggests that space and time are quantized, meaning they are made up of tiny discrete units. This quantization could prevent the universe from reaching infinite density, allowing for a cosmic bounce instead of a singularity. In the standard Big Bang model, the universe began from a singularity, where all matter and energy were concentrated at a single point of infinite density. This singularity represents a breakdown in our understanding of the laws of physics, as general relativity cannot describe what happens at such extreme conditions. However, the concept of a cosmic bounce offers a way to avoid the singularity and extend the universe's history beyond the Big Bang. In the cosmic bounce scenario, the universe undergoes a phase of contraction before reaching a minimum size. Instead of collapsing into a singularity, quantum effects cause the universe to bounce back into an expansion phase. This bounce represents a transition between the contraction and expansion phases, allowing the universe to avoid the singularity and continue evolving. The concept of a cosmic bounce, the idea that the universe may contract and then bounce back into an expansion phase, avoiding a singularity, has gained traction in modern cosmology, particularly through theories like string theory and loop quantum gravity. These theories provide alternative ways to think about the universe's behavior during extreme conditions, such as the Big Bang or a potential Big Crunch, when the universe's density and temperature are incredibly high. Both approaches offer mechanisms that could prevent the universe from collapsing into a singularity, a point of infinite density where the known laws of physics break down. In string theory, the universe's fundamental components are not zero-dimensional point particles, as envisioned in classical physics, but rather one-dimensional vibrating strings. These strings vibrate at different frequencies, giving rise to the various particles and forces we observe in the universe. Additionally, string theory posits the existence of multiple dimensions, beyond the familiar 3 spatial dimensions and 1 dimension of time, which further complicates our understanding of space, time, and gravity. One of the key insights from string theory is that the presence of these strings could alter how gravity behaves under extreme conditions. As the universe contracts and approaches the point where a classical singularity would form, the vibrational nature of strings introduces new forces that resist further collapse. These forces could prevent the formation of a singularity by causing the universe to bounce instead. In this way, string theory offers a potential solution to the singularity problem, suggesting that a cosmic bounce could lead to a new expansion phase without the need for an infinite density state. This bouncing behavior in string theory is also connected to the idea of brane cosmology, where our universe is thought to exist on a 3-dimensional membrane, or brane, floating in a higher dimensional space. According to some models, the universe might undergo cycles of expansion and contraction due to interactions between branes in higher dimensional space. When branes collide, it could trigger a Big Bang-like event, initiating a new phase of cosmic expansion, followed eventually by another contraction. The cosmic bounce, in this context, would be the result of a brane collision rather than the universe collapsing into a singularity. Similarly, loop quantum gravity, LQG, offers a different framework for understanding how space and time behave under extreme conditions. LQG is an attempt to reconcile general relativity, which describes the behavior of large-scale objects like stars and galaxies, with quantum mechanics, which governs the behavior of subatomic particles. One of the central ideas in loop quantum gravity is that space and time are not continuous, as traditionally thought, but are instead composed of discrete, finite units, often referred to as quanta of spacetime. These discrete units are incredibly small, on the order of the Planck length, about 10 mass to 35 meters, but they provide a fundamental structure to space and time. In the context of a contracting universe, LQG suggests that spacetime cannot be compressed indefinitely. As the universe contracts and its density increases, the discrete nature of spacetime becomes more pronounced. Instead of collapsing into a singularity, the universe reaches a point where quantum effects dominate, preventing infinite density from occurring. This process could lead to a cosmic bounce, where the universe transitions from contraction to expansion without reaching a singular state. Loop quantum gravity's approach to the cosmic bounce contrasts with the classical view of a big crunch, where the universe's contraction inevitably leads to a singularity. Instead, LQG proposes that as the universe approaches the Planck scale, quantum gravitational effects cause a rebound, or bounce, allowing the universe to expand again. This idea offers a solution to the singularity problem while also opening the door to cyclical models of the universe, where each bounce represents the start of a new cosmic cycle. Both string theory and loop quantum gravity provide promising avenues for understanding the early universe and avoiding the problem of singularities. In string theory, the vibrational nature of strings and the existence of higher dimensional branes offer new forces that prevent collapse, while loop quantum gravity's discrete units of spacetime provide a natural limit to how much the universe can be compressed. These ideas suggest that rather than a singularity marking the end of the universe, a cosmic bounce could lead to a new beginning, allowing the universe to go through endless cycles of contraction and expansion. The concept of a cosmic bounce is supported by both string theory and loop quantum gravity, which offer mechanisms to prevent the universe from collapsing into a singularity. In string theory, the presence of vibrating strings and higher dimensional branes introduces new forces that could cause the universe to bounce, while in loop quantum gravity, the discrete nature of spacetime prevents infinite density, leading to a bounce instead of a singularity. These theories not only address the singularity problem, but also open up the possibility of a cyclic universe, where the cosmos undergoes repeated phases of expansion and contraction, potentially offering a more complete understanding of the universe's evolution. The cosmic bounce offers an elegant solution to the problem of the singularity and provides a natural explanation for what might have existed before the Big Bang. If the universe has undergone multiple cycles of expansion and contraction, then the Big Bang was not the beginning of time, but simply the beginning of the current cycle. Time extends infinitely into the past, with each bounce representing a new phase in the universe's evolution. One of the key features of the cyclical universe theory is that it suggests the universe is in a constant state of flux, undergoing repeated cycles of creation and destruction. Each expansion phase gives rise to galaxies, stars, and planets, while each contraction phase destroys them, only for the process to begin anew after a cosmic bounce. This cycle of destruction and renewal has been a central theme in many philosophical and religious traditions, which have long viewed time as cyclical rather than linear. In the cyclical universe, destruction is not seen as an end, but as a necessary precursor to new creation. As the universe contracts, galaxies and stars are pulled together by gravitational forces, eventually collapsing into a dense state. But instead of reaching a singularity, the universe undergoes a bounce, triggering a new expansion phase. In this sense, the universe is constantly being reborn from the ashes of its previous self. The idea of cosmic cycles of destruction and renewal also resonates with ideas in thermodynamics and entropy. According to the second law of thermodynamics, the total entropy of a closed system always increases over time, leading to a state of maximum disorder or heat death. In the standard model of cosmology, this heat death represents the ultimate fate of the universe, where all matter and energy are evenly distributed and no more work can be done. However, in the cyclical universe model, each contraction phase resets the universe's entropy. As the universe collapses into a dense state, it erases the entropy accumulated during the previous expansion, allowing for a fresh start with each new cycle. This process of resetting entropy ensures that the universe can continue undergoing cycles of creation and destruction indefinitely, without ever reaching a final state of maximum disorder. The concept of eternal cosmic cycles challenges our understanding of time and the nature of existence. In the standard model, time has a beginning and an end, with the universe evolving from a singularity to an eventual heat death. But in the cyclical universe, time is infinite, with no true beginning or end. The universe has always existed and will continue to exist, constantly evolving through cycles of creation and destruction. The cyclical universe and cosmic bounce theory offer a compelling alternative to the traditional Big Bang model. By proposing that the universe undergoes repeated cycles of expansion and contraction, this theory avoids the need for a singularity and provides a natural explanation for what might have existed before the Big Bang. The oscillating universe model suggests that time extends infinitely into the past and future, with each cycle representing a new phase in the universe's evolution. The cosmic bounce offers a way to transition between contraction and expansion phases, preventing the universe from collapsing into a singularity. Finally, the enduring cycles of destruction and renewal present a dynamic view of the universe, where creation and destruction are intertwined in an eternal cosmic dance. Cosmic inflation is one of the most transformative ideas in modern cosmology, providing a framework for understanding the conditions that shaped the universe during its earliest moments. This theory explains the astonishing expansion that occurred just after the Big Bang, offering answers to some of the most perplexing questions about the universe's structure and origins. Inflation not only accounts for the universe's rapid growth, but also opens up possibilities beyond the Big Bang itself, including ideas about multiple universes and the nature of time and existence. In this chapter, we will explore the remarkable expansion of the universe, the potential for realities beyond the Big Bang, the quantum vacuum's role in universe formation, and how these concepts are reshaping our understanding of time and existence. The theory of cosmic inflation, proposed by Alan Guth in 1981, suggests that during the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing at a rate far faster than the speed of light. This period of inflation is believed to have occurred approximately 10⁻36 seconds after the Big Bang and lasted until about 10⁻32 seconds. During this incredibly brief period, the universe expanded by a factor of at least 10⁻26, meaning that regions of space that were once microscopic in scale were stretched to sizes much larger than our observable universe today. This astonishing expansion helps to resolve several key problems that the traditional Big Bang theory struggled to explain, such as the horizon problem, the flatness problem, and the absence of magnetic monopoles. The horizon problem refers to the question of why different regions of the universe, which should not have been in contact with each other, have nearly the same temperature and density. Inflation solves this by proposing that all regions of the universe were once in close contact before they were rapidly stretched apart, leading to a uniform temperature across vast distances. The flatness problem concerns the observation that the universe appears to be geometrically flat on large scales, meaning that the angles of a triangle add up to 180 degrees and that parallel lines never meet. Without inflation, this flatness would be difficult to achieve, as even a slight deviation in the universe's curvature would have led to a much different geometry over billions of years. However, the rapid expansion caused by inflation would have smoothed out any initial curvature, resulting in the nearly flat universe we observe today. Finally, inflation explains the apparent absence of magnetic monopoles, hypothetical particles that would carry a single magnetic charge. According to some theories, these particles should have been produced in large quantities during the early universe, yet none have been observed. Inflation suggests that any magnetic monopoles that were created were diluted by the rapid expansion of the universe, becoming so spread out that they are extremely rare or non-existent within our observable universe. One of the most profound implications of cosmic inflation is the possibility that the Big Bang was not the true beginning of everything. Instead, inflation offers a window into a larger reality that may have existed before the Big Bang or even continue to exist alongside it. In the inflationary model, the universe's exponential expansion could be just one part of a much larger process that gives rise to multiple universes, a multiverse. In this context, inflation may be an eternal process, with different regions of space inflating at different rates. Some regions, like our observable universe, have exited the inflationary phase and settled into a more stable state, while other regions continue to inflate, creating new bubble universes in the process. Each bubble universe could have different physical properties, governed by different laws of physics. This leads to the possibility of a vast multiverse where countless universes exist, each with its own unique characteristics. The multiverse hypothesis, which arises naturally from inflationary theory, fundamentally changes our understanding of the Big Bang. Rather than a singular event that marked the beginning of all existence, the Big Bang might be just one instance in an infinite sequence of universe creation. This opens up the possibility that what we think of as nothing before the Big Bang might actually be part of a larger, ongoing cosmic process, with universes constantly being born and evolving within the multiverse. One of the most intriguing aspects of inflation is its connection to quantum mechanics, particularly the concept of a quantum vacuum. The quantum vacuum is not empty in the traditional sense. Rather, it is a seething field of energy where particles constantly appear and disappear due to quantum fluctuations. These fluctuations are a fundamental feature of quantum fields, and they play a crucial role in the inflationary model. During the inflationary period, quantum fluctuations in the inflationary field were stretched to macroscopic scales as the universe expanded. These fluctuations provided the seeds for the large-scale structures we observe today, such as galaxies and clusters of galaxies. Tiny variations in the density of matter caused by quantum fluctuations were amplified by inflation, leading to the formation of stars, galaxies, and other cosmic structures as the universe continued to evolve. The idea that the universe could emerge from a quantum vacuum challenges traditional notions of causality and creation. In this view, the universe did not necessarily need a cause in the classical sense. Instead, it could have arisen spontaneously from the quantum vacuum through a process known as quantum tunneling. This process allows particles, or in this case, entire universes, to tunnel through energy barriers, emerging into existence without violating the laws of physics. This idea, known as quantum genesis, suggests that the universe could have been born from the quantum vacuum without the need for a singular Big Bang event. Instead, the quantum vacuum provides the potential for universes to emerge, driven by the same quantum fluctuations that shape the behavior of particles at the smallest scales. This leads to the possibility that our universe is just one of many that have emerged from the quantum vacuum over time. The concept of quantum genesis also aligns with the multiverse hypothesis, as it suggests that multiple universes could be created from the quantum vacuum, each with its own set of physical laws and constants. In this view, the quantum vacuum is a vast sea of potential, where universes constantly bubble into existence through the process of quantum tunneling. This challenges the traditional view of the universe's creation and suggests that the process of universe formation is ongoing, with no true beginning or end. Cosmic inflation and the quantum vacuum not only reshape our understanding of the early universe, but also challenge our traditional views of time and existence. In the standard model of cosmology, time is viewed as a linear progression, with a clear beginning at the Big Bang and an inevitable end, either through a big freeze, big crunch, or big rip. However, inflation and the multiverse introduce new possibilities for how time and existence might function on cosmic scales. In the context of eternal inflation, time does not have a singular beginning or end. Instead, time could extend infinitely into the past and future, with universes constantly being created in different regions of space. This challenges the idea that the Big Bang was the beginning of time and suggests that time itself might be an emergent property of the inflationary process. In this view, what we perceive as the beginning of time is simply the point at which our particular universe exited the inflationary phase and began to evolve in a more stable manner. This new perspective on time also raises questions about the nature of existence. If time extends infinitely into the past and future, then the universe, or multiverse, may have always existed in some form, constantly cycling through phases of creation and destruction. This cyclical view of time aligns with some ancient philosophical and religious traditions, which view time as a never-ending loop rather than a linear progression. Inflation also offers new insights into the nature of existence itself. In the traditional view, the universe is a singular entity, governed by a fixed set of physical laws. But in the multiverse, existence becomes much more diverse and complex. Each universe within the multiverse may have its own set of physical laws, leading to vastly different realities. Some universes might resemble ours, while others could be entirely alien, with different dimensions, forces, and forms of matter. This new view of existence challenges our classical understanding of reality and suggests that what we perceive as real is just one possible version of reality within a much larger multiverse. In this context, existence is not a singular, fixed state, but a dynamic and ever-changing process, shaped by the interplay of quantum fluctuations, inflation, and the laws of physics. Cosmic inflation and the early universe conditions provide a revolutionary framework for understanding the universe's birth and evolution. The astonishing expansion of the universe during inflation explains many of the mysteries that the traditional Big Bang model could not, while also opening up possibilities for realities beyond the Big Bang. The quantum vacuum and the emergence of universes from quantum fluctuations offer new insights into how universes form and challenge traditional notions of causality and creation. Finally, the new perspectives on time and existence introduced by inflation and the multiverse theory suggest that the universe is far more complex and dynamic than previously thought, with time and existence taking on new cyclical forms that stretch beyond the boundaries of our observable universe. Singularities, black holes, and the enigmatic nature of the universe's origins are central themes in modern cosmology. These concepts challenge our understanding of space, time, and the fundamental laws of physics. A singularity represents a point where density and gravity become infinite, causing the laws of physics as we know them to break down. Both black holes and the Big Bang are associated with singularities, making them key elements in discussions about the universe's formation and evolution. In this chapter, we explore the state of the universe before the Big Bang, the role of black holes in cosmic evolution, and how string theory may offer new insights into singularities and the universe's origins. One of the most profound mysteries in cosmology is the state of the universe before the Big Bang. According to the standard model of cosmology, the Big Bang represents the beginning of time, space, and matter. Before this event, there was nothing, no time, no space, and no physical laws as we understand them. However, The theory of singularities, derived from Einstein's general relativity, suggests that before the Big Bang, the universe existed in a state of infinite density and temperature, known as a singularity. A singularity is a point where the curvature of space-time becomes infinite, and the gravitational pull is so strong that not even light can escape. In the context of the Big Bang, the entire universe was compressed into this singular point before it rapidly expanded, creating the space, time, and matter we observe today. This leads to the perplexing question: if the universe was in a singular state before the Big Bang, what, if anything, existed before that? And can we ever truly understand the nature of this singularity? The laws of physics, as we currently understand them, break down at the singularity, meaning that we cannot describe what happens at that point using classical physics. General relativity, which governs the behavior of space, time, and gravity, cannot be applied to the conditions at the singularity because it predicts infinite quantities that are not physically meaningful. Similarly, quantum mechanics, which describes the behavior of particles at the smallest scales, also struggles to account for the extreme conditions of a singularity. This breakdown of physical laws at the singularity has led many cosmologists to question whether the singularity was truly the beginning of everything, or if it simply represents a boundary in our current understanding of the universe. Some theories suggest that the singularity could be a transition point between different phases of the universe's evolution, such as in the cyclic universe model, where each phase of contraction is followed by a bounce into a new expansion. Others propose that quantum gravity, a yet-to-be fully realized theory that combines general relativity with quantum mechanics, could provide insights into the nature of the singularity and what might have existed before the Big Bang. While singularities are most commonly associated with the Big Bang, they are also present in black holes, another cosmic mystery that has fascinated scientists for decades. A black hole forms when a massive star collapses under its own gravity, compressing all of its mass into a singularity. Like the singularity associated with the Big Bang, the singularity at the center of a black hole represents a point of infinite density and gravitational pull. The gravitational force of a black hole is so strong that not even light can escape from it, making black holes invisible to direct observation. Despite their elusive nature, black holes play a crucial role in shaping the universe. They influence the evolution of galaxies, as their intense gravitational fields can pull in nearby matter, shaping the formation of stars and other cosmic structures. Supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way, are thought to be essential in the growth and development of galaxies. Black holes are also closely connected to the study of singularities, as the center of a black hole, known as the event horizon, leads to a singularity where space-time curvature becomes infinite. This makes black holes a natural laboratory for studying the nature of singularities and the extreme conditions they represent. Understanding black holes could provide valuable insights into the conditions that existed during the early moments of the universe's formation, as the same principles of singularities apply to both black holes and the Big Bang. One of the most intriguing connections between black holes and the universe's evolution is the idea that black holes may be linked to the formation of new universes. Some theoretical models suggest that when matter falls into a black hole, it is compressed into a singularity, but instead of simply vanishing, it could form the seed of a new universe. In this scenario, black holes could act as cosmic gateways between different universes, with each black hole leading to a new universe with its own set of physical laws and constants. This idea aligns with the multiverse hypothesis, which proposes that multiple universes exist within a larger cosmic structure. While general relativity has provided profound insights into singularities, it is not the final word on the subject. Singularities represent a breakdown in our current understanding of the laws of physics. And to fully understand them, we need a theory that can combine general relativity with quantum mechanics. This is where string theory comes into play. String theory is a theoretical framework that seeks to unify the forces of nature by proposing that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings that exist in multiple dimensions. In string theory, singularities may not be true points of infinite density, but rather regions where the fabric of space-time becomes stretched and deformed by the presence of these tiny strings. String theory suggests that at the smallest scales, space and time are not continuous, but are instead made up of discrete units, much like the pixels on a computer screen. This quantization of space-time could prevent singularities from forming, as the universe would never reach infinite density. One of the most promising aspects of string theory is its ability to incorporate extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. In the standard model of cosmology, the universe is described as a 4-dimensional space-time, but string theory suggests that there could be additional hidden dimensions that we cannot directly observe. These extra dimensions could play a crucial role in shaping the behavior of singularities and the universe's evolution. For example, string theory introduces the concept of branes, short for membranes, which are multidimensional objects that can exist in higher dimensional space. According to some versions of string theory, our universe exists on a 3-dimensional brane that floats in a higher dimensional space known as the bulk. In this framework, singularities could represent points where branes collide or interact, leading to the creation of new universes. String theory also offers new insights into the nature of black holes. In classical general relativity, the singularity at the center of a black hole is a point where the curvature of space-time becomes infinite. However, in string theory, the singularity may be replaced by a more complex structure, known as a fuzzball, which is made up of vibrating strings. This fuzzball structure could prevent the formation of a true singularity, offering a new way to understand the extreme conditions inside a black hole. The idea of fuzzballs represents a major shift in our understanding of black holes and singularities. In classical general relativity, the event horizon of a black hole marks the point of no return, beyond which nothing can escape. However, in string theory, the event horizon could be a more dynamic and complex structure, made up of strings and branes. This could offer a solution to the information paradox, a long-standing problem in black hole physics that arises from the apparent loss of information when matter falls into a black hole. String theory suggests that information is not lost, but is instead encoded in the complex structure of the fuzzball, preserving the fundamental principles of quantum mechanics. In addition to offering new ways to understand black holes, string theory also provides a framework for understanding the universe's origins. In traditional cosmology, the Big Bang is seen as the beginning of time, space, and matter, but string theory suggests that the Big Bang could be just one event in a much larger and more complex cosmic process. For example, the ekpyrotic model, which is based on string theory, proposes that the universe was created from the collision of 2 branes in higher dimensional space. This collision released an immense amount of energy, leading to the rapid expansion of the universe and the creation of matter and energy. The ekpyrotic model offers an alternative to the traditional Big Bang singularity by suggesting that the universe did not begin from a singular point of infinite density, but from a collision between branes in higher dimensional space. This eliminates the need for a singularity and provides a natural explanation for the conditions that existed before the Big Bang. In this model, time and space extend infinitely into the past and future, with brane collisions representing transitions between different phases of the universe's evolution. String theory's ability to unify general relativity and quantum mechanics also offers new insights into the nature of time and existence. In classical physics, time is viewed as a linear progression, with a clear beginning at the Big Bang and an inevitable end in the distant future. However, string theory suggests that time could be cyclical or even multidimensional, with different regions of space-time governed by different physical laws. This challenges our traditional understanding of time and opens up new possibilities for how the universe might evolve. Singularities, black holes, and cosmic mysteries are central to our understanding of the universe's origins and evolution. The singularity before the Big Bang represents a boundary in our current understanding of physics, while black holes offer a unique window into the nature of singularities and the extreme conditions they represent. String theory provides a promising framework for resolving these mysteries by offering new ways to understand singularities, black holes, and the universe's origins. By unifying general relativity and quantum mechanics, string theory opens up new possibilities for how the universe might evolve and what might have existed before the Big Bang. The universe is a vast and mysterious expanse, and despite the advances made in cosmology, much of it remains unseen and unknown. Two of the greatest mysteries are dark matter and dark energy, which together account for roughly 95% of the universe's total mass energy content. While dark matter is thought to provide the gravitational framework that holds galaxies and clusters of galaxies together, dark energy is believed to be driving the accelerated expansion of the universe. These invisible forces play a crucial role in shaping the structure and fate of the universe. In this chapter, we explore the gravitational influence of dark matter, the role of dark energy in the universe's accelerated expansion, how dark matter contributes to the formation of galaxies, and the complex interplay between dark matter and dark energy. Dark matter is one of the most significant components of the universe, accounting for approximately 27% of its total mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. However, its presence is inferred from its gravitational effects on visible matter, such as stars and galaxies. Dark matter provides the unseen scaffolding that supports the large-scale structure of the universe, ensuring that galaxies remain bound together and do not fly apart due to their rotational speeds. The concept of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving too quickly for the amount of visible mass present. He hypothesized that there must be some unseen dark matter providing additional gravitational force to keep the galaxies in the cluster from dispersing. In the decades since Zwicky's discovery, further evidence has been found to support the existence of dark matter, particularly through the study of galaxy rotation curves. In a typical spiral galaxy, stars closer to the center should orbit faster due to the greater gravitational pull from the dense core, while stars farther from the center should orbit more slowly, much like the planets in our solar system. However, observations show that stars in the outer regions of galaxies orbit at the same speed as those near the center, indicating the presence of an additional gravitational force, dark matter, that extends beyond the visible edges of the galaxy. Dark matter's gravitational influence is also evident in the phenomenon of gravitational lensing, where the light from distant objects, such as galaxies or quasars, is bent by the gravitational field of massive objects between the light source and the observer. The amount of bending observed often cannot be accounted for by the visible matter alone, suggesting that dark matter is responsible for the additional gravitational pull. Although dark matter does not interact with electromagnetic forces, hence its invisibility, it interacts gravitationally with ordinary matter and plays a crucial role in holding galaxies and galaxy clusters together. Without dark matter's gravitational influence, galaxies would not have the mass required to remain bound, and the universe as we know it would not exist in its current form. While dark matter provides the gravitational framework for the universe's structure, dark energy is responsible for driving its accelerated expansion. Discovered in the late 1990s through observations of distant Type Ia supernovae, dark energy is thought to account for about 68% of the universe's total energy content. Unlike dark matter, which exerts a gravitational pull, dark energy appears to have a repulsive force, pushing galaxies apart and causing the expansion of the universe to speed up over time. The discovery of dark energy was a revolutionary moment in cosmology, as it overturned the long-held belief that the universe's expansion was slowing down due to gravity. Instead, observation showed that the universe's expansion has been accelerating for the past several billion years, suggesting the existence of a mysterious force, dark energy, that counteracts gravity and drives this acceleration. One possible explanation for dark energy is that it is a property of space itself. According to Einstein's theory of general relativity, empty space is not truly empty, but has energy associated with it. This vacuum energy could be responsible for the accelerated expansion of the universe. However, the exact nature of dark energy remains unknown, and it represents one of the greatest challenges in modern physics. The accelerated expansion of the universe due to dark energy has profound implications for the universe's ultimate fate. If dark energy continues to dominate the dynamics of the cosmos, the universe will continue expanding at an ever-increasing rate, leading to a scenario known as the Big Freeze, or heat death, where galaxies, stars, and planets drift apart, and the universe becomes cold and dark as all available energy is spread thinly across an ever-expanding space. Dark matter and dark energy, while distinct phenomena, both play critical roles in the evolution and structure of the universe. Dark matter provides the gravitational pull necessary to form galaxies and galaxy clusters, while dark energy drives the universe's expansion, shaping its large-scale structure over time. Together, these forces create a delicate balance that governs the fate of the cosmos. Dark matter plays a fundamental role in the formation and evolution of galaxies. In the early universe, shortly after the Big Bang, matter was distributed relatively evenly across space, with small fluctuations in density. These fluctuations were seeded by quantum processes during the inflationary period and eventually grew into the large-scale structures we observe today. However, ordinary matter alone was not sufficient to form galaxies and galaxy clusters. Without dark matter, the gravitational forces generated by ordinary matter would not have been strong enough to overcome the pressure of the early universe's radiation, and matter would have remained dispersed rather than coalescing into dense regions. Dark matter provided the additional gravitational pull necessary to amplify these initial density fluctuations, allowing regions of higher density to attract more matter and form galaxies. As dark matter does not interact with light or other forms of electromagnetic radiation, it did not experience the same pressure from radiation as ordinary matter, enabling it to collapse into structures more quickly. This led to the formation of dark matter halos, which provided the gravitational framework for galaxies to form around. These dark matter halos continue to play a crucial role in galaxy evolution. In spiral galaxies like the Milky Way, dark matter extends far beyond the visible edge of the galaxy, forming a halo that stabilizes the galaxy's rotation and prevents it from flying apart. In galaxy clusters, dark matter binds the galaxies together, preventing them from dispersing due to their individual motions. Simulations of cosmic structure formation that include dark matter closely match the observed distribution of galaxies in the universe. These simulations show that dark matter is essential for explaining the large-scale structure of the cosmos, including the formation of galaxy clusters, superclusters, and the cosmic web, a vast network of filaments and voids that spans the universe. While dark matter helps explain the structure and formation of galaxies, the relationship between dark matter and dark energy is complex and remains one of the most intriguing aspects of modern cosmology. Dark matter's gravitational pull works to hold galaxies and clusters of galaxies together, while dark energy drives the universe's accelerated expansion, pushing galaxies apart. The interplay between these two forces determines the large-scale structure of the universe and its ultimate fate. In the early universe, dark matter played a dominant role in shaping the cosmos, as its gravitational pull overcame the expansion caused by the Big Bang. This allowed galaxies and galaxy clusters to form and grow over billions of years. However, as the universe expanded and became less dense, dark energy began to take over, accelerating the expansion and causing galaxies to move apart more rapidly. The balance between dark matter and dark energy is a delicate one. While dark matter dominates the dynamics of individual galaxies and galaxy clusters, dark energy governs the expansion of space on cosmic scales. As the universe continues to expand, dark energy will eventually overpower dark matter's gravitational pull, leading to an increasingly empty and cold universe. One of the key questions in cosmology is how dark matter and dark energy will evolve over time. If dark energy remains constant, the universe will continue expanding at an accelerated rate, leading to a big freeze. However, if dark energy changes over time, it could lead to different outcomes, such as a big rip, where the expansion becomes so rapid that galaxies, stars, and even atoms are torn apart. Alternatively, dark energy could decay or reverse, leading to a big crunch, where the universe collapses back in on itself. Dark matter and dark energy are two of the most mysterious and important components of the universe. Dark matter provides the gravitational framework that holds galaxies and galaxy clusters together, while dark energy drives the universe's accelerated expansion. Together, these forces shape the large-scale structure of the cosmos and determine its ultimate fate. While much about dark matter and dark energy remains unknown, their interplay is critical to understanding the universe's evolution and structure, and future research may reveal more about the nature of these elusive forces. The origin of the universe and the concept of nothingness touch on some of the deepest philosophical and existential questions humanity has ever faced. Beyond the scientific explorations of cosmology and physics lies a realm of reflection that grapples with the fundamental nature of existence, the limits of human understanding, and the search for meaning in an often indifferent cosmos. The question of what, if anything, existed before the Big Bang, or whether the universe emerged from nothing, challenges not only physical theories, but also philosophical traditions. In this chapter, we will explore the philosophical implications of nothingness, the existential reflections on human significance in the vast universe, the limitations of our understanding of time and existence, and how existentialism seeks to find meaning in a universe that seems to offer little certainty. One of the most profound challenges in philosophy is grappling with the idea of nothingness. The very concept of nothingness, the absence of anything including matter, energy, space, and time, raises difficult questions about the nature of existence and creation. What does it mean for something to emerge from nothing? And if nothingness is truly a void, how could it have the potential to give rise to the entire universe? In ancient philosophy, thinkers like Parmenides argued that nothing cannot exist, because to even conceive of nothingness, there must be something. In his view, the notion of nothingness was a logical impossibility, and the universe had always existed in some form. Similarly, in the context of modern cosmology, the idea of the universe emerging from nothing challenges the traditional boundaries of cause and effect. How can the universe, with all its matter and energy, come from a state of absolute nothingness without a cause or precursor? The question of nothingness also intersects with religious and metaphysical debates about creation. Many religious traditions hold that the universe was created by a divine being or force, often from nothing, in a process known as creatio ex nihilo, creation out of nothing. This idea posits that a supernatural force transcends the material universe and has the power to bring it into existence. However, from a philosophical standpoint, this explanation leaves many questions unanswered, particularly regarding the nature of the creator and the state of existence prior to the act of creation. Philosophically, the idea of nothingness challenges our understanding of causality and existence itself. In classical physics, every event is caused by a previous one, leading back through an unbroken chain of cause and effect. But if the universe truly arose from nothing, then this chain is broken at its origin. The absence of a prior cause defies the logic of classical causality, suggesting that the universe's creation may lie beyond the reach of human comprehension. In addition to the challenges of nothingness, the vastness of the universe brings into question the significance of human existence. In a universe that stretches across billions of light years, with countless stars and galaxies, the place of humanity can seem profoundly insignificant. This theme has been explored deeply in existentialist philosophy, which grapples with the tension between the apparent indifference of the universe and the human desire for meaning. Furthermore, the concept of time becomes even more problematic when we consider the possibility of multiple dimensions or a multiverse. String theory, for example, proposes that there may be additional dimensions of space-time beyond the 3 spatial dimensions and 1 temporal dimension that we experience. These additional dimensions could contain entirely different timelines or forms of existence, further complicating our understanding of time. If time is not an absolute linear progression, but rather something that is flexible and dependent on perspective, then our attempts to understand the beginning of the universe, or even the concept of before the Big Bang, may be inherently flawed. Our understanding of existence, therefore, may be limited not only by the physical laws of the universe, but also by the cognitive structures that shape how we perceive reality. In addition to the philosophical challenges posed by time, the concept of existence itself remains elusive. What does it mean for something to exist? Can existence be reduced to the material and observable, or is there something more fundamental that underlies the physical world? These questions have been central to metaphysical debates throughout history, and they take on new significance in the context of modern cosmology. The philosophical reflections on nothingness and existence challenge our understanding of the universe, time, and human significance. The concept of nothingness raises difficult questions about causality and creation, while existentialism grapples with the search for meaning in a universe that seems indifferent to human life. The limits of human understanding, particularly concerning time and existence, remind us that our attempts to comprehend the cosmos may always be constrained by our cognitive and perceptual frameworks. Despite these challenges, existentialist philosophy offers a way forward, suggesting that meaning is not something to be discovered, but something to be created through individual experience, choice, and action. In the vast and mysterious cosmos, the quest for meaning remains one of humanity's most profound and enduring pursuits.